Hello everyone, we are Alex, Isaac, and Taeyeon. Today we will showcase an example and provide an in-depth analysis of cross-selling in the insurance industry. For our project, we utilized a dataset in which a health insurance company sought to determine the interest and likelihood of their current policy owners purchasing a new product, vehicle insurance. Our dataset consists of a mix of categorical and continuous features related to the client's vehicle history, and the target is a binary value, whether the client is interested in vehicle insurance or not. So why should companies be interested in cross-selling? The cross-selling of related products is an area of great interest to many companies for which it is crucial to be able to gauge public interest in new products. Cross-selling can also help improve customer satisfaction and build loyalty between the customer and provider. Particularly, the COVID-19 pandemic encourages further studies into the subject, as consumers seek budget-friendly and reliable coverage. We tested various algorithms to find the most efficient model in solving this problem, and this initially required data cleaning and feature selection.
First, we converted the three categorical features, gender, vehicle age, and vehicle damage, into either binary or ternary values, and then normalized the data to a mean of 0 and a standard deviation of 1. We also dropped the feature containing customer ID from the dataset. We calculated the Pearson correlation and created a heat map to visually see if correlations between features themselves or between features and the response label existed. And as you can see on the slide, the majority of the correlations have an absolute value below 0.5, so we did not have to drop any features due to redundancy. On the other hand, you can see that the vintage feature seems to be random noise. Charting the target labels for each value of the feature, we can see that it is pretty much random, so we created a second dataset without it. Then, we split the datasets using a 0.7, 0.3 train test split. Finally, we analyzed the target value distribution and noticed that the target labels are unbalanced, with about 87% being zeros. Because of this, we decided to optimize for the F1 score instead of accuracy or area under the curve. Looking at previous attempts by others on Kaggle, we can see that the best improvements in accuracy are about 1%, while the F1 value can be significantly increased. This makes sense in terms of the application to the real world as well, as we would put a lot more value on missing an interested customer.
We tried 4 models: logistic regression, decision tree, gradient boosting, and random forest. We chose these models based on the nature of features being a mix of binary and continuous values, and the target value being a binary value. We utilized the k-fold cross-validation technique to perform hyperparameter tuning for each model and both datasets, with and without the noisy feature. The first observation is that the logistic regression model did not manage to perform well on F1 score, probably due to the data not being very well linearly separable. For this reason, we dropped this model from further results. The second observation is that removing the noisy feature highly increased the performance of random forest, while the other two models were very slightly hurt by the change. Since the decrease was not too big, we decided to continue without the feature. The third observation we made is that random forest performed worse than just a simple decision tree. After further testing, we found that decreasing the number of estimators of random forest increased the F1 score. This is probably because the target labels are unbalanced, so averaging many trees makes it more likely that we will predict a 0 for every entry, thus decreasing the F1 score. Running our final models on the test data, we find that gradient boosting does slightly better than the decision tree, with random forest being significantly below both for the aforementioned reasons. Plotting the precision recall curve, we see very similar results, with gradient boosting being slightly in the lead. For completeness, we also graphed the ROC of the three models, even though we do not expect good performance, since our models have been optimized for F1 score. One thing that we can notice is that random forest disadvantage for F1 score became an advantage here, as it performed much better in terms of AUC. This would make random forest a great middle ground between F1 score and AUC.
Comparing our results to others on Kaggle, our model performs at the same level as others using similar techniques, but falls behind compared to the more advanced ones as we do not utilize state-of-the-art models or advanced data processing methods. For the final report, we will continue optimizing our approaches and incorporate more powerful models like Light GBM and Cap Boost, our goal being an F1 score of 0.4 on the test data. Thank you for watching.